off with Andrew Bodling and Anupam Sharma from the Department of Aerospace Engineering at the Iowa State University. The title of the talk is The Investigation of Noise Reduction Mechanisms in a Bioinspired Airfoil. And so now we are all pretty curious what bioinspired is. The floor is yours.
Hello everyone, so I'm Andrew Bodling. I'm currently a PhD student at Iowa State University, and in today's presentation I'll be discussing the work in my paper titled Investigation of Noise Reduction Mechanisms in a Bioinspired Airfoil. Before I start, I just want to acknowledge my co-author, Anupam Sharma. The owl is a fascinating animal. It is known to be silent in both flapping and gliding flight. One species in particular, the barn owl, is especially adept in silent flight. In fact, it cannot be heard until it is within 3 meters of its prey. One of the anatomical features that plays a role in reducing noise is the soft downy coat. Clark and his colleagues studied the downy coat and found it consists of fine hairs that vertically rise up and then plateau out, forming a canopy structure as seen on the top of forests. So they wondered, if this canopy structure could reduce noise from owl wings, could it also reduce noise from things like wind turbines and jet engines? So they created the designs shown here, which are called finlets. There's 2 variations, the fences and the rails. They found that by using these finlets, they were able to significantly reduce the noise from the trailing edge. But the question, based off the results, they formed some hypotheses for why the noise was reduced. However, to validate these hypotheses, high-resolution simulations are required. Therefore, in our work, we're looking to simulate the fence geometry with both high spatial and temporal resolution, which will allow us to fully understand the noise reduction mechanisms. In addition, we're looking to use these simulations to help understand how the finlets affect the drag and lift on the airfoil. So now into the numerical methodology. So for the flow solver, we use FDL 3DI. This is the compressible implicit LES Navier-Stokes solver from the Air Force. For the space derivatives, it uses compact 6-order finite difference schemes. For the time integration, it uses the implicit Beam-Norman scheme, which is 2nd order. For the acoustic solver, we solve the Fox-Williams-Hawkins equation in the frequency domain. The frequency domain formulation is shown in the equation here, where we neglect the volume integral term in order to increase the computational efficiency of a solver. This is valid since we have low Mach numbers. The solver was previously validated for monopole, quadrupole, and dipole point sources, and some of the results for that is shown here. So now into the baseline of geometry. So to create the baseline grid, we start with a NACA double O2O cross-section geometry, and then we extrude a single O-grid block from the airfoil surface up until 110 chords away from the airfoil. The span is made to be 6% of the chord. We use a Reynolds number of 500,000, an angle of attack of 0 degrees, and a Mach number of 0.2. We trip the boundary layer at 5% of the chord. The grid metrics and wall units are shown here, where our y plus value is less than 1, and our x and z plus value are relatively low as well. So since we're interested in high Reynolds number applications, where transition occurs very early, we trip the boundary layer with a geometry resolved tripwire, as shown in the middle figure. By doing this, we have very early transition, and we have turbulent flow that mimics these higher Reynolds number flows. So how accurate is our baseline simulation? Well, to assess the accuracy, we can compare our span average CP and CF values from our simulation to Xfoil as well as available experimental data. Looking at the CP and CF distributions, we see good agreement with Xfoil as well as the experimental data. So we can also look into the time average velocity and Reynolds stress profiles that are span averaged. The velocity profile at different core-wise locations is shown in the figure on the left. We see here that the viscous sublayer is well resolved. Looking into the log region, we see that our slope is slightly different than the value obtained from the von Karman constant. However, note that the experiments from Lee and Kahn had a very similar slope in their measurements, where they had a NACA 0012 at a very similar Reynolds number. Looking also at the Reynolds stresses, where we compared it in this plot to two different high-fidelity simulations, and we see good agreement in all the Reynolds stresses. So now into the baseline and fence geometry comparisons. So on the left, we have the fence geometry used in the experiment. In the two figures here, we have the two different ways that we modeled this geometry in our simulations. One was with a single-step geometry, and the other was with a stair-step geometry. Now, in order to define this in our solver, we first started with a collection of points on our structured grid, and then we identified points that were basically points that were eye-blanked, and so the solver knew that at those points it did not solve the governing equations. And then the adjacent points, shown in the blue, were defined as no-slip boundaries. Now, a very similar procedure was done also with the stair-step. So this is a single step. With the stair-step, we defined it as shown there. Note here that our fence mesh is identical to the baseline other than these holes that we've introduced into the mesh. This avoids any grid-to-grid differences in our results. So before assessing the acoustics, it's important to make sure that the drag and lift is not affected by these fences. So in the table here, we have the drag coefficients for the baseline and the fences. We see with the stair-step fence, we have an increase of around 3%. With the single step, it's much more, it's about 9%. Note though, that with both fences, the drag increase is much less than the increase in the wetted area. So we know from a Mead's trailing edge noise model that surface pressure fluctuations are associated with more far-field noise. The spectra on the left plot here shows the spectra for the baseline, the single fence, and the stair-step fence. We see that at the higher frequencies we have reductions in the SPL of the fences compared to the baseline. We have a slight increase in the SPL at these lower frequencies. Now, how does this compare to the experiment? Well, here we have a very similar fence configuration in their experiments, and we see a qualitative agreement in the delta SPL among all frequencies. Now into the noise reduction mechanisms. So we take our LES data near the airfoil, and we use our acoustic solver to predict the far-field noise at an observer that is 90 degrees, which is basically right on the top of the trailing edge, directly above it. So shown here is that prediction, where we see that with the single step, there's no significant difference, the red and black. However, with the stair-step fence, there is a significant reduction in the far-field noise along a high range of frequencies. So how does this compare to the experiment? Well, using also a similar fence configuration from Clark, we have agreement from 1 to 4 kilohertz. We have this large reduction And from 4 to 5 kilohertz, we have a little to no reduction. So we have some agreement here. So why are we getting these reductions though? So from the experiment, they formed 2 hypotheses for why the noise was reduced. The first one is that the fences are lifting up the energy-containing eddies away from the scattering edge, shown by this cartoon here. The other hypothesis is that the fences, they break up the eddies and reduce the Spanwise coherence, shown by the cartoon here. So let's now test these with our simulation. So on the right-hand side here, we have a TKE field for the baseline and the stair-step fences. We see near the airfoil, the TKE is much less with the fences. Above the fences, however, we have a much higher TKE field. This is shown more quantitatively, or more clearly, by span averaging the data. So here we have the TKE profile upstream of the fences, and then we have the TKE at the trailing edge. We see upstream of it, there's no significant difference, but once again we see near the airfoil we have a reduction with the fences, and we have an increase above the fences. And note here that y over h is basically the normalized distance. So y over h is 1. Y over h, when it's 1, that's basically the top of the fences. So we see that increase here. Now you'll see from the plot that we have a larger increase with the single-step fence, shown by the red. So keeping in account the predictions in the Farfield noise, we believe that the blunt leading edge of the single-step fence is offsetting any benefits from this increased source trailing edge separation. So let's look at the second hypothesis, the Spanwise coherence. So here we have the Spanwise coherence at 2 different frequencies, and we see at the lower frequency we have a reduction in the Spanwise coherence once the separation distance is larger than the fence spacing, delta S. However, at the higher frequency, there's really no significant difference. So in conclusion, the aero performance did not significantly change with the fences. We had a Farfield noise reduction of up to 10 decibels. We identified 2 noise reduction mechanisms, the source trailing edge separation and the Spanwise coherence reduction at low frequencies. And we saw there was no Farfield noise reduction with the single-step fence, which is likely due to the additional turbulence generated from the fence leading edge and also the additional scattering at the fence leading edge. In future work, we want to analyze the D96 for direct comparison with the data. I was going to acknowledge the funding shown here, and as well as collaborators and support that we've had. Thank you. Are there any questions?
Thank you very much. The questions, we have plenty of time. Yes, please.
You mentioned your delta depth class for this Spanwise spacing was about 15, is that right?
Yeah, it was about 0.01. What's it? It's about 0.01. Is this, you mean spacing for the fences?
No, the grid resolution.
The what?
Grid resolution.
Grid. Yes.
That was that class.
Oh yes, there was very low delta Z.
That's about 15. Well, so in terms of a fence, how wide is this fence in plus coordinates?
I know it's about 1% of the height. It's very, very, very thin. We basically use the thinnest possible fence width. Because we know from experiments that the larger the fence width is, the less reductions you get in your Farfield noise.
Yeah, so my question is, are you resolving the flow around that fence if it's so thin?
Well, we do know the Z plus near the top of the fences is around 30, so it's not significantly different than the baseline Z plus, which is about 17, or the max is anyway. So the max of the fence near the walls of it is about 30, and for the baseline it's only about 17. So So it's not a significantly different Z plus value.
Sorry, I missed the difference between the single step and the stair step geometry.
Yes. So basically, with the single step, we have so it didn't come out too well on this predicate here, but with the single step fence, you have the final height of the fence is reached in one abrupt step. With the stair step, you have several steps, so it slowly reaches that final height, which better matches the actual experiment, as you see on the left side here. It's a gradual increase.
And do you expect some artifact in the fact that you don't have like a continuous line, but it's a stair step instead? I mean, is the key factor the fact that the height is not constant, or the fact that you have the stairs?
I believe the key factor is breaking up the coherence of the structures and gradually breaking those up.
The coherence can be broken by the two geometries. The Spanwise direction is inspect the difference between the two fences, if the spacing is the same.
Actually, I'll look into it. Oh, I understand.
A quick question. You mentioned that simulation was done at Reynolds number 500,000, and you used a trip wire to induce turbulence because the real flow is at higher Reynolds number. Why do you have to do that? Why can't you just simulate the higher Reynolds number?
Well, as we have higher Reynolds number, makes sense. We're using wall-resolved simulations here, so we're not using any kind of turbulence model. So in order to resolve the very small scales that you get at those higher Reynolds number, you need a very, very large grid. I think maybe we can go up to 1 million if we used a overset meshing approach. I mean, in the future we'll do that to see how better matches. But that is a good point, but yeah, we are limited of how high we can go, but that's something we try. Overset meshing.
More questions? I have one or two. The first one is, have you changed the speed of flow? So what is the change? Well, if you change the speed of flow, does the effect changes with the speed? So
we only use
what is your flow speed, by the way? Maybe I missed that.
We never did any variation with the Mach number. We
Yes.
use a constant Mach number. So
And what was the Mach number?
0.2, which is
0.2.
similar to experiments. They had a 0.15.
Okay.
So actually, the experiment also didn't investigate the change in the effects of the Mach number, but that's something that could be looked into in the future.
Okay. And a second question, I was a bit surprised to see that there is no impact, or you said that there is no impact on the aerodynamics, because if you think of the geometry there, what you build is a thicker trailing edge, and this is known to change the aerodynamic performance. So I was wondering why you didn't find it in your calculations. Is it because you changed also the length of the airfoil slightly bit, so you make it longer? So is it a fair comparison? So how did you compare the original airfoil with your treated airfoil?
So
in terms of aerodynamics, how did you do that?
Well, I compared my baseline calculations with X-foil in order to make sure that was the right number. And then we did a surface integration in order to calculate the forces acting on the fences. It's important to note that with these fences, it maintains the symmetry of the airfoil because it's the same height on both sides. So therefore, the lift wasn't affected. Although this is a zero lift case, though, so so we would need to do a higher angle attack to see if those are affected.
Okay, maybe the reason is that it's a zero. Okay. I think we move on to the next presenter. Thank you again.